بسم الله الرحمن الرحيم. هدف اللايف هاد انه ما راح اشرح صراحة، راح احل لانه علي بكرة تكنيكلي بكرة يوم April 2nd كويز في التوبكس الموجودة في عنوان الفيديو هاد، وكمان فوق على بلاس ترانسفورم، فلازم اشتغل بسرعة. بس انه وانا بحل راح اشرح، يعني مش in depth، بس انه fair enough، الشرح يكون fair enough. طيب، فهذا الفيديو اكتر شي راح يفيد الناس اللي مثلا already فهمانين، طيب بس بدهم حدا انه يحل قدامهم عشان بس يتعودوا على اللوجيك. وهو انا already يعني هي اول مرة ترى بحل، يعني انا فهمت الشابترز او فهمت التوبكس وهلا عم ببدأ احل، فيعني اذا غلطت او سويت شي يعني it's fine. ف مش انه fully rely on me، بس انه you can I guess. فبلا طيت كلام، عم بفكر انه اسحب على suggested problems، لانه صراحة هدول تخيل هدول اخذ منه ما بعرف كم 3 ساعات، وترى الشابترز 2 chapters هدول 6 7، كل واحد ممكن ياخذ كتير وقت، يعني finding the eigenvalues، بعدين من كل eigenvalue you find an eigenvector it would take forever. فبحاول انه نسحب عليهن. طيب هي سكرناهن ونحل previouses من دكتوري دكتور خالد. يس هدول اتوقع كويزز تبعون spring 26 اللي هو last semester. اوكي، اول شي ممكن اعطيكم هيك نبذة بسيطة، يعني شو هو الايجن فاليو والايجن فيكتور. الايجن فاليو الايجن فيكتور is a vector v that if we multiply it by a matrix A, it will give me the same vector scaled by some constant lambda. This lambda we call it an eigenvalue. V we call it an eigenvector. فبس هاي هي الايجنفاليو والايجنفector. So eigenvector is a vector that if we multiply it by a matrix A, we get the same eigenvector scaled by some constant. So it's a number, it's a number. We call it an eigenvalue. Each eigenvalue corresponds to some eigenvector or eigenvectors بالأصح eigenvectors، لأنه ممكن الايجنفاليو الواحد يعطيك أكثر من eigenvector. We'll see some examples. What else? خليني أفتح النوتات تبعيتي. Let's see if I have something I would like to say before starting. Okay, now how do we solve? So let me remove these two circles and let's take this to the other side. So A V minus lambda V equals 0, right? Now take V as a common factor. So notice we take it not like this, because this is a vector, like we can express it as a column matrix. So it's a matrix, you know, in matrices the order of multiplication matters. So the V, when you take it as a common factor, it will become here. It matters actually. So A minus lambda equals 0. So this way we took column matrix V as a common factor. column matrix V as a common factor. Nice. Next, notice that lambda is a number, as we said before. So it's been deduced, or not deduced, like نقص من matrix A. So it's subtracted from matrix A. But we can't do subtraction between matrix and a number. So to solve this issue, we can multiply this number by the identity matrix. So A minus lambda I times the eigenvector equals 0. So the identity matrix follows the same size as matrix A. So if matrix A is an n by n matrix, then matrix I is an n by n. And if the كانت A 3 by 3, then the identity matrix is also 3 by 3. So let's say the identity matrix is 3 by 3. So 1 0 0 0 1 0 0 0 1. And we're multiplying lambda by the identity matrix. So what will we get? Okay, lambda times 0 times 0 times 0 times 1 times 0 times 0 times 0 times 1. So we'll get lambda 0 0 0 lambda 0 0 0 lambda. Now we can do subtraction. So let's say this is matrix A. So this is A11, A12, A13, A21, A22, A23, A31, A32, A33. Now we can do A11 minus lambda, and these won't change because they're subtracted by 0. A22 minus lambda, and A33 minus lambda. So basically, if you don't want to show all of the work like in details, you can just subtract the main diagonal of matrix A by lambda. So A11 minus lambda, A22 minus lambda, A33 minus lambda. Okay? Now we want to find wait, hold up a second. Okay. If the coefficient matrix, this is the coefficient matrix now, it's the coefficient of the eigenvector. If the coefficient matrix has an inverse, it means the determinant of A minus lambda I does not equal to 0. If that's true, then the only solution will be the 0 vector. The 0 vector will be the only solution in this case, if the determinant of the coefficient matrix is not equal to 0, like if it's invertible. So the only solution will be the 0 solution. But we have a very important rule that the 0 vector is not considered as an eigenvector. It's not considered as an eigenvector. So to get eigenvectors, to find eigenvectors, we need the opposite. What's the opposite of the determinant not equal to 0? Being equal to 0. إن شاء الله أنت صح. إنه عكس إنه ما تكون 0، إنه تكون 0. So we need to find the determinant and we equal it to 0. Then we get an equation that's equal to 0. This equation, we call it the characteristic equation, we solve for lambda, which is the eigenvalue. Then we substitute it in this equation, and then we find the eigenvectors. We reduce the matrix, as we'll see in a couple of minutes. We reduce the matrix, reduce it to to reduced echelon form, and we get some eigenvectors. The eigenspace is the set of all possible eigenvectors. So the eigenvectors that I will find form a basis, so they are part of the span function. So let's say I get v1, v2, and v3. So these are eigenvectors. They form a basis for the span function for the eigenspace. So we write v1, v2, v3. So any linear combination of these eigenvectors are part of the eigenspace. So the eigenspace is the set of all all possible eigenvectors. We can form these all possible eigenvectors using the basis. We get the basis from solving this equation, like finding the eigenvectors. So we plug it in the span function, and the span function will do the rest, like finding the rest of all possible eigenvectors, and we put it into a set. This set is called the eigenspace. So that's basically the eigenspace. Each eigenvalue has an eigenspace. We denote it by this. So each eigenvalue will give you some eigenvectors. These eigenvectors form an eigenspace. So the eigenvectors corresponds to some eigenvalue. This eigenvalue has an eigenspace. This eigenspace contains the vectors, the eigenvectors corresponding to the eigenvalue. So each eigenvalue, بالمختصر, each eigenvalue has its own eigenspace. The eigenspace contains the eigenvectors that corresponds to the eigenvalue that we get from that eigenvalue. Okay. We have some properties for eigenvalues that the product of the eigenvalues after we get some, let's say we have a matrix A. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or let's keep it 2 by 2. 1, 2, 3, 4. So, we have some properties for the eigenvalues. Let's say we got the eigenvalues for this matrix, lambda 1 and lambda 2. So the first one is, if we multiply the eigenvalues, like we do lambda 1 times lambda 2, this will give me the determinant of matrix A. It's not magic. Well, it is kind of. ما بعرف ليش بس إنه if you multiply them, you'll get the determinant of A. If you combine them, you'll get the trace of A. I guess it's TRA, the trace of A. If you combine the eigenvalues, you get the trace of A. If you multiply them, you get the determinant of A. What's the determinant here? It's 4 minus 6, it's negative 2. So if you multiply lambda 1 and lambda 2, which are the eigenvalues for matrix A, you'll get negative 2. And if you combine them, you'll get, what's the trace here? It's 4 plus 1, like the sum of the entries on the main diagonal, so it's 5. If you combine them, you'll get 5. Okay, so again, if you multiply, let's say lambda n, you will get the determinant of A. If you combine them, you'll get the trace of A. Now we have a special case for triangular matrices. You know what a triangular matrix is, right? You have upper and lower triangular matrices where the main diagonal, this is 1 1 2 2 3 3, you have like some values here, and below it there is 0, so this is a lower, or no wait, is it upper or lower? It's upper. This is an upper triangular matrix, so the main diagonal, below it there are zeros, so this is an upper triangular matrix. The lower, it's like the exact opposite, so A11, A22, A33, and we have some values here, and the zeros are above the main diagonal, so this is the main diagonal, and the zeros are here, so this is a lower triangular matrix. So what's special about these triangular matrices is that the eigenvalues are just the entries on the main diagonal. So the eigenvalues for this upper triangular matrix is A11, lambda 2 is A22, and lambda 3 is A33. Same thing for this. So each eigenvalue, as we said, will give you some eigenvectors. And every time after finding an eigenvector, we check the equations. So let's say we got some eigenvectors v1. We check it using this equation, the original definition that I introduced you to at the beginning of this live session. So A times vector v, or column matrix v, AV equals lambda v. So the process is to find lambda, then to find the corresponding v, the eigenvector that corresponds to lambda, and then after finding an eigenvector, we check it. We do matrix A times v equals the lambda that we found times the v. If they are equal, then v is a valid eigenvector. If not, then we made a mistake. Then it's not valid. Okay. For 2 by 2 matrices, let's say we're talking about A minus lambda I matrix, the coefficient matrix. If it's a 2 by 2, so let's say 3 minus lambda, 2 minus lambda, 1, 0, let's say. So the characteristic equation, which is the determinant of A minus lambda I, will be a quadratic equation. You can verify this. So multiply, you'll get lambda squared. 3 times 2 is 6. 3 times 2 minus 3 lambda minus 2 lambda. So minus lambda squared minus 6 lambda plus 6. So verify that this is a quadratic equation. So the degree of the characteristic equation depends on the dimension of the coefficient matrix A minus lambda I. So if it's a 3 by 3, then I get a cubic characteristic equation. If it's a 2 by 2, I get a quadratic. If it's a 4 by 4, I get a quadruple, whatever, يعني to the power of 4. Algebraic multiplicity and geometric multiplicity, I'll talk about them later when we start solving. And yeah, that's it. This I'll talk about it while solving. Yeah, let's start solving, because this is a lot of information. You have to digest a bit, and the best way to digest some information is by applying, by solving. So let's see. I have to explain the diagonalizable thingy. Okay, yeah, I have to explain this concept first. So, what do we mean by testing if, or let's say, again, how to determine if matrix A is diagonalizable or not? Diagonalizable or not? So we have 3 theorems. The first one, if you got okay, let's say that A is an n by n matrix. It's a square matrix that has a dimension of n by n. If you got n linearly independent eigenvectors, then it's diagonalizable. This is the first one. The first check, the first theorem to determine if it's diagonalizable or not. You use any of the 3, you don't have to prove all of them. But if A is an n by n matrix, if you got n linearly independent, مثلا كان 3 by 3, if you got 3 linearly independent eigenvectors, then it's diagonalizable. The second one, if matrix so after we find the eigenvalues and eigenvectors, we get something called geometric and algebraic multiplicity. So if the geometric multiplicity equals the algebraic multiplicity for every eigenvalue, then our arrow diagonalizable. Whatever. This is the second one. So for every eigenvalue, it has properties. Every eigenvalue has 2 properties: geometric multiplicity and algebraic multiplicity. They are just numbers. They're whole numbers, 1, 2, 3. So if for every eigenvalue of matrix A, let's say I got lambda 1, okay, lambda 1 equals 2, lambda 2 equals 3, lambda 3 equals 5, and the geometric multiplicity and algebraic multiplicity. For lambda 2, we got geometric multiplicity of 5 and algebraic multiplicity of 5. Here we got 2, 2, 2, or like 3, 3. So for every eigenvalue, the geometric multiplicity equals the algebraic multiplicity for every eigenvalue. Now, if one of them, at least one of them, is not the same, like let's say the geometric multiplicity was 1, then it's not diagonalizable. Okay? The last one, but it's like the weakest one to prove, because students often misuse it. So the instructors likes to use these two, not the last one, but it's worth mentioning. It's valid, but you have to be careful when using it, because it's one way. You can't do it like if and only if. It only goes one way. So it says for matrix A, which is an n by n matrix, if you got n distinct eigenvalues, then it's diagonalizable. So in this case, eigenvalue number 1 was 2, eigenvalue number 2 was 3, eigenvalue number 3 was 5. So they are distinct. 2, 3, 5. They're distinct. They're not equal. None of them are repeated. Like it's not 2, 2, 5. It's 2, 3, 5. So all of them are distinct numbers, distinct eigenvalues. So if we got this form, and n by n, like let's say matrix A is 3 by 3. So we get 3 distinct eigenvalues, then matrix A is diagonalizable. But the opposite is not true. If we got 2, 2, 5, this doesn't mean that matrix A is not diagonalizable. So that's the issue with this theorem. Because some students may think if they don't get n distinct eigenvalues, then it's not diagonalizable. No, it's not the case. You can still, like if you have this case, it can still be diagonalizable. So you have to continue. You have to prove this, either this or this. So one of them being repeated doesn't imply that the matrix is not diagonalizable. But all of them being distinct, 100%, you can deduce that it's diagonalizable. So it goes one way only. So these are the 3 conditions, or like 3 theorems to judge whether matrix A is diagonalizable or not. So that's basically diagonalizability. So we now know how to judge if A is diagonalizable or not. But what if the question continues and asks you to diagonalize matrix A? So matrix A is diagonalizable, but we want to diagonalize it now. So what do you mean by diagonalizing matrix A? It means to show that we can write matrix A as P, D, P inverse. What are P, D, P inverse? They're just 2 matrices, P and D. P inverse is just the inverse of matrix P. So matrix P is a matrix of the eigenvectors of A. So let's say we got lambda 1, lambda 2 from matrix A, and we got V1, V2 as these are the eigenvalues for matrix A, and these are the corresponding eigenvectors. This corresponds to eigenvalue 1, and this corresponds to eigenvalue 2. So matrix P is just the eigenvectors written as columns. So this eigenvector, let's say it's 1, 0, 1, and eigenvector 2 is 1, 1, 1. So we write it as 1, 0, 1, 1, 1, 1. This is matrix P. We write the eigenvectors of matrix A as columns in matrix P. And what about matrix D? It's a diagonal matrix. So you know diagonal matrices have all zeros except the main diagonal. So let's say 1, 1, 1, 0, 0, 0, 0, 0, 0. So this is a diagonal matrix. This is the identity matrix, in fact, but it is a diagonal matrix. It has all zeros except the main diagonal, so we call it a diagonal matrix. Same thing, D is a diagonal matrix, and the entries on the main diagonal, we put the eigenvalues of matrix A. So 1 and 2, and the rest are zeros. That's it. That's matrix D. Notice that the eigenvalues are written in the same order. So you know, eigenvector 1 corresponds to eigenvalue 1. Eigenvector 2 corresponds to eigenvalue 2. Same thing. Eigenvalue 1 is written in column 1, so the corresponding eigenvector for eigenvalue 1 should be written in column 1. Same thing, eigenvalue 2 corresponds to the second column, which we write the eigenvector 2 that corresponds to eigenvalue 2. So the order here matters. If you write eigenvalue 1 here, you will write eigenvector 1 here. If you write eigenvalue 2 here, you will write eigenvector 2 here. Okay? And since we can write it in this form, we can say that A is similar to matrix D. A and D are similar matrices. What's special about similar matrices that they have the same characteristic equation, they have the same eigenvalues with the same algebraic multiplicity, the same eigenspace dimension, just the dimension, not the eigenvectors, only the dimension, like the number of bases of the span set. They have the same determinant, rank, nullity, and trace. So every diagonalizable matrix A is similar to a diagonal matrix D. So we first start by judging A if it's diagonalizable or not. If it's diagonalizable, then it's similar to a diagonal matrix D. So A and D are diagonalizable if A is diagonalizable. Then we can write it in this form. Okay? And we prove it, actually we don't write it like this when proving it. We multiply by P both sides. Sorry, it's the order matters. So P, we multiply it on the right, so P multiplied on the right. So we get AP equals P, and P inverse is the identity matrix, so P times D. So we multiply matrix A with P and matrix P with D. We multiply these two and see if they equal to each other. If they equal to each other, then it's diagonalizable. So we showed that it is no, not diagonalizable. Like we showed the diagonalization of matrix A. What else? Oh nice, شرحته بنص ساعة. Okay, good enough. good enough. Okay, let me give you some of chapter 7. Yeah. Okay, so for chapter 7, we want to solve some system of differential equations. So previously, we were working with a single differential equation. Now we're working with a system of differential equations. So they are in the form of x prime t equals a times x. X is a vector here. So matrix A is multiplied by vector x, which is a matrix as well. So notice that if we multiply these two, we'll get a system of differential equations. So the solution for this is xt, right? We like the whole objective for this course is to find xt or yt or y or x equals. You know, now it's x of t this time. They like to denote it as x, and the independent variable is t. So whatever, it doesn't matter really. So it's in the form of c1 e to the lambda 1 t v1 plus c2 e lambda 2 t v2 plus c3 e lambda 3 t v3 plus cn e lambda n t vn. So let's break it down step by step. C is just a constant. We can find it if the question gives us some initial condition. So let's say x of 0 equals some 1, 2, 3. So this way we can put 1, 2, 3 instead of x of t, and instead of t we can put 0 and find c values, c1, c2, cn. So these are just c's, like constants, as we did before. Lambda 1 is the eigenvalue number 1, so eigenvalue 1. Lambda 2 is eigenvalue 2. Lambda 3 is eigenvalue 3. And v1 is eigenvector that corresponds to eigenvalue 1. v2 is the eigenvector 2 that corresponds to eigenvalue 2. v3 is the eigenvector 3 that corresponds to eigenvalue 3. vn is the eigenvector n that corresponds to eigenvalue n. And t is just t, the independent variable. E is just e. So it's cn, let's see here, cn multiplied by e to the eigenvalue multiplied by t times the corresponding eigenvector. That's it. We just combine them. So basically, matrix A, we find its eigenvalues and eigenvectors. Then we plug them in this solution. This is a solution to the system of differential equations. So we plug them in here, and if the question gives me an initial condition, we just substitute it here. Instead of t, we get 0, and we solve for c. Now the solution can be compressed into one matrix. So it's x1t, x2t, xnt. So it's better to, combine all of the solutions into one single matrix. If the solution is complex, if the eigenvalues are complex, then the solution would look like, or like we prefer it to look like, a real part plus I, which is the imaginary part, plus the imaginary part. Sorry, x and t. So if the eigenvalues are imaginary, here if the eigenvalues are real, here if it's imaginary, or like complex, if you like this word better, we prefer to write it as the real part plus I, the imaginary part. And that's basically it. The rest is just solving. I hope this brief explanation to chapters 6, 7 was helpful. I just summarized all of the main ideas. Now we start solving. I'm just checking if I missed something. Like main concepts. Of course I missed some small details, but these will come when I solve. Okay. Inshallah I didn't miss anything. So let's start. نقول بسم الله. I'm just worried about this. Can I remove this? Okay, maybe if I closed this and I open it again. Oops, my private files. Yeah, it's gone. Yeah, it's better, much better. The slider was gone. Yeah, now it's back. It's gone. Okay. Yeah. What do we have here? My private files again. Sorry. يلا تعالوا. Previouses, quizzes. Let's start with. This was. I don't know. What is this? Orthogonal. No, that was chapter 4. This one. Yeah, that's what we opened. Okay. Determine whether or not the following matrix is diagonalizable. If it is, find a matrix P and a diagonal matrix D such that A equals P, D, P inverse. P is invertible, and find AP and PD. Okay, cool. That's a lot of stuff actually. Okay. How to approach this question? First, we need to find the eigenvalues of matrix A. So, to find the eigenvalues of matrix A, we want A minus lambda I. So that's matrix A, but we subtract lambda from the main diagonal. So 1 minus lambda. Okay, 1 minus lambda, negative 1, 0, negative 1, 2 minus lambda, negative 1, 0, negative 1, 1 minus lambda. Okay. Next, we want to find the determinant of A minus lambda I. So let's expand along row 1. So that's 1 minus lambda multiplied by, okay, let's 2, ولا أقول لك خلاص, by this determinant. So what's the determinant? It's this 2 minus lambda. Oops. حكى الدكتور انه on every parentheses you forget, you lose a mark, I guess. 2 minus lambda, 1 minus lambda, minus -1 times 1 is 1. So that's the first one. So this is plus, this is minus. Minus is plus. So plus 1 times this matrix, this. That's basically lambda minus 1. So I just change the order of this. Minus 0. So again, we do minus lambda equals. Where's my calculator? A second. في واحد أخذ الكالكوليتر تبعي أو إني أنا مضيعه وينه bruh مو وقته. This is my calculator. bruh. Okay, مش مشكلة. I can use this. Oh no, wait. Is it on my back? No. Okay, whatever. ما لقيته. خلاص لقيته. Found it. No need for this. Because it takes time to input. Okay, 1 minus lambda on 2 minus 2 lambda minus lambda plus lambda squared plus lambda minus 1. So that's 1 minus lambda lambda squared minus 3 lambda plus 2 plus lambda minus 1. Now we distribute. Oh my, what is this? I can't skip not distributing. Okay, lambda squared minus 3 lambda plus 2 minus lambda cubed plus 3 lambda squared minus 2 lambda, then plus lambda minus 1. Combine like terms, we have negative lambda cubed, lambda squared plus 2 lambda squared, 3 lambda squared, يعني 4 lambda squared, so that's gone, that's gone. Negative 3 minus 2, that's negative 5 plus 1, negative 4. So that's gone, plus 1. Now we equal it to 0. Remember, we equal the determinant of a minus lambda I to 0. I have to show you this because it's important. First, it's a good practice to keep the coefficient of like the main leader, let's say, as positive. So we multiply both sides of the equation by negative. So lambda cubed minus 4 lambda squared plus 4 lambda minus 1 equals 0. Yep. And degree of 3. 1, negative 4, 4, negative 1. Oh my. Am I doing something wrong? Yeah, I'm doing something wrong actually. What did I do? Wait, 1 minus lambda. That's understandable. Let's check. 1 minus lambda, negative 1, 0, negative 1, 2 minus lambda, negative 1, 0, negative 1, 1 minus lambda. Okay, cool. We expand along this. 1 minus lambda, 2 minus lambda times 1 minus lambda minus 1. Okay, cool. Plus 1. That's lambda minus 1 minus 0. Okay, cool. Here it's 2 minus 2 lambda minus lambda plus lambda squared. Oh, I forgot the plus 1 here. For that small minus 1, it made such difference. Man. Minus 1. So that's 2 minus 1, which is 1. That's 1. So that's 1. And 1 minus 1 is 0. So we don't have this term. Okay. Let's try again. Let's put 0 here. So we get, yes, we get lambda 1. Lambda 1 equals 2. Lambda 2 equals 0. Whoa. Okay, we have a problem here. What's the problem? That we have a cubic equation and we get 2 roots. Like the calculator only gives me 2 roots. So one of these 2 roots is being repeated, but which one exactly? That's the issue. We don't know. Is it the 2? Is it the 0? We don't know. So how do we know? We perform synthesis or like synthetic division. ما بعرف كيف بكتبوها هيك أتوقع. I think so. Okay. So this is basically minus 2 and lambda, right? Oh, sorry, this one is easier. Without the synthesis, this one is easier. Like, you don't need it actually. This one I can factor out lambda and get lambda squared minus 4 lambda plus 4 equals 0. So that's lambda equals 0 already done. That's lambda 1. Lambda 2 and lambda 3 will be from this quadratic equation. So 1 minus 4, 4, that's 2. So the 2 is repeated. You see, only 2 appeared here. I'm sure it's the 2 that's been repeated. So we got this synthesis marvelous, man. So these are the eigenvalues. That's one tiny bit of information we got for this question. We continue. Okay. Now I need another slide. Sorry. I need another slide. to continue for the eigenvectors. So these are the eigenvalues. Now it's time to find the eigenvectors. So basically the eigenvectors, you take each one, let's start with eigenvalue 0. You take each one and basically substitute it here. You see this lambda, you substitute 0 instead of lambda. Bas. And you equal it to 0, so you add another column of zeros and you reduce it. You solve the system of equations using row reduction method. So that's it. So 1 minus 0 is just 1. 2 minus 0 is 2. 1 minus 0 is 1. So 1, 2, 1. 1 minus 0 is 1. 2 minus 0 is 2. 1 minus 0 is 1. And as I said, you add another column of zeros and you reduce it. So that's 0, 0, 0. Oh, you know, remember the three, because one of the questions was to determine whether or not the following matrix is diagonalizable. So the third one, if you got n distinct eigenvalues, then it's diagonalizable. So we have 0, 2, 2. It's not distinct. 2 is repeated. But does this mean that it's not diagonalizable? No, we should continue actually. We can't conclude that it's not diagonalizable just from 2 being repeated. It doesn't work like two ways. It only works one way. So that's why we're continuing. We start by negative r1 plus r2. Oh no, actually r1 plus r2. That's it. So we get, oops. Okay, fine. We just combine them. So 1 plus negative 1 is 0. Negative 1 plus 2 is 1. 0 plus negative 1 is negative 1. And 0 plus 0 is 0. Next, we combine row 2 with row 3. So delete row 3. And then 0 plus 0 is 0. 1 plus negative 1 is 0. Negative 1 plus 1 is 0. 0 plus 0 is 0. And you can do, well, actually it doesn't matter actually, because if you mess with the row, then this will change. خلاص, leave it as it is. You name this x, y, z, but notice that x has a pivot, y has a pivot, but z doesn't. So z is a free variable. So we call it, let's say, s. So it's x minus, or x minus y equals 0. So this means x equals y, and y minus z equals 0. So y equals 0. Sorry, y equals z. And z is s. So z is s. So y is s. And x is s. Because y is s, so x is s. Next, you write x, y, z equals, or second. Let's write it here. X, Y, Z. What's X? It's S. Y is S. Z is S. You take S as a common, the free variable out, you get 1, 1, 1. So that's the eigenvector. Now, each time you get an eigenvector, you have to check AV equals lambda V. So, where is A? This is matrix A. So let's take a screenshot of it. Now, in my opinion, if your work is correct, you don't have to check صراحة. It's a quiz that's like 30 minutes long. I won't be checking صراحة. Okay. This is a 3x3, and this is 3x1. So the result is 3x1. So 1 times 1 plus negative 1 times 1 plus 0 times 1 is 0. Negative 1 times 1 plus 2 times 1 plus negative 1 times 1 is 0. 0 times 1 plus negative 1 times 1 plus 1 times 1 is 0. So it's 0, 0, 0, 0. Okay. Now lambda times V. Where is lambda? It's 0, right? You multiply 0 by 1, 1, 1. What do you get? 0, 0, 0. So 0, 0, 0 equals 0, 0, 0. Then this is satisfied. So that's basically for lambda 1. Now you repeat the same process for lambda 2. Unfortunately, there is no workaround it. Okay. So 1 minus 2 is negative 1. Two minus 2 is 0. And 1 minus 2 is negative 1. So 0, negative 1. Again, you have to add a column of zeros, and you solve the system of equations. 0, 0, 0. Okay. Now you reduce it. First, I'll multiply row 1 by negative 1. So that's 1, 1, 0, 0. Let's multiply row 2 by negative as well. So that's 1, 0, 1, 0. And okay, yeah. 0, negative 1, negative 1, 0. Let's row 1, like negative row 1 plus row 2. So, oops. So negative 1 times 1 plus 1 is 0. Negative 1 times 1 plus 1 is, negative 1 times 1 plus 0 is negative 1. And negative 1 times 0 plus 1 is 1. And 0. Next, you can let's multiply negative R2 by a negative, like rho 2 by a negative. That's 1 and negative 1. Next, let's add rho 2 to R3. So 1 plus negative 1 is 0. And negative 1 plus negative 1 is negative 2. And then if we divide rho 3 by negative 2, we get 1. Then if we do R3 plus R2, then we get, where do I put this? Just put this here. Oops. Yeah, fair enough. Yeah. So this is 0. And that's it. That's the best I can do. Or maybe I can, yeah, I can do negative here and cancel this. So that's one last reduction. So that's 0. So let's say this is x, y, z. Oh, all of them has what? XYZ equals XYZ, wow. Or like, wait. X equals 0, y equals 0, and z equals 0. Nice. So 0, 0, 0. Yeah, you can say that. But let's check. Let's check. Wait, how did the 0 change? Okay. Let's check. So A times V equals lambda V. So let's multiply matrix A. Where's matrix A? Matrix A times V. So 1 times 0. Oh, it's all zeros. So but if we multiply 2 by this, yeah, it's zeros as well. But wait, eigenvectors can't be 0. So this is not an eigenvector. This is a matrix of zeros, so it's not. shouldn't be. It's excluded المفروض. Did I make a mistake somewhere? Let's see. Eigenvector equals 0. Okay, cool. We got 1, 1, 1. Oh, we got something else. Wait, hold up a second. I was solving... What? No, how? Okay, that's cool. 1, -4, 4. لا تقول لي I made a mistake somewhere. No. Okay, negative lambda cubed plus 4 lambda squared minus 3 lambda minus 2 plus 1 is -4 يا الحبيب. -3 lambda minus 1 من وين جاب هاي؟ what؟ ماني فاضي صراحة debug. خلاص أعطي إجابة خلاص. is my solution correct? Please say yes. Not quite, man. يا الله. وين الغلط؟ طيب oh yeah, okay. You know, minus lambda times 1 هي لأنه كانت 2 فهذا اللي خربط فهون 1 minus 1 lambda. Okay, it makes sense. So that's minus 3 lambda. It makes sense now. أخي غلط بسيط ممكن يخرب عليك. So that's plus 3. And the correct eigenvectors should be 1, -4, 3, 3 and 1. 3 and 1. So let's say this is 1 and 3. So let's go down. You see, when I check the eigenvector, that's the benefit of checking. I didn't get quite the answer, you know. So that's 1. Okay, so 1 minus 1 is 0. Negative 1, 0. Negative 1. 2 minus 1 is 1. Negative 1, 0, negative 1. 1 minus 1 is 0. واو 0 0 0 0 نيجاتيف ونيجاتيف 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 1 بالنص كمان ما شاء الله شوي سجادة مش ماتريكس. اوكي switch row 1 with row 2 ما فيني صراحة. let's copy it and we take these we switch it وبالمرة كمان خليها كمان negative. So switch and make it negative. So negative. This is R2. خليها كمان negative R1. بعد ما تسوي switch خلي R1 negative. So that's negative. And this is 1 1. Next, what do we do? Yeah, we do negative R2 plus R3. Let's move this. So that's 0 0 0. And then what do? We do negative R2. So that's took. And then what do? We do R2 plus R3. Now I forgot to add the additional row of zeros, but it's fine. You can add it at the end. It doesn't change that much. So if you forgot it, it's fine. Now you can add it, مثلا it's fine, zeros. Or you don't even have to. خلاص, if you know that you need to equal to 0, that's the whole point. X, Y, Z, but now Z doesn't have a pivot, so we call it S. So it's X plus Z equals 0. So it's X equals negative Z. And Y equals 0. And Z equals S. So here it's negative S. So X, Y, Z is equal to X is negative S, this is 0, this is S. If we take S as a common factor, we get a negative 1, 0, 1. Now you have to check it. AV equals lambda V. A is this. So let's check. Negative 1 times 1 plus 0 times negative 1 plus 0 times 1. It's negative 1. Negative 1 times negative 1 plus 2 times 0 plus negative 1 times 1. 0. 0 times negative 1 plus 0 times negative 1 plus 1 times 1 is 1. And if we multiply lambda by this, well, lambda is 1. So lambda times this is the same thing, so it's equal. So yes, it's correct. Last but not least, lambda 2 after lambda 3 equals 3. You see, it's a very long question. We didn't even start, That's just finding the, I don't know, man. It's so long. well, I would dedicate the half of the exam to solve this. Not joking. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 1 minus 3 is negative 2. Negative 2, negative 1, negative 2. Okay. Now you reduce it. Well, let's switch R1 and R2. And you multiply R1 with negative. So you get boom, 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 boom. And since you multiplied it by negative, boom, boom, boom. Next you do 2R1 plus R2. Boom. R1 plus R2, so that's 0. 2 times 1 plus negative 1 is 1. 2 times 1 plus 0 is 2. Then R2 plus R3. I see a row of zeros. That's 0, 0. Yeah, that's it. You can't do anything else. Now you can add the row of zeros now. After the column of zeros. So that's 0, 0, 0. This is x, y, z. Z is the pivot. Sorry, it's the free variable since it doesn't have a pivot. X plus y plus z equals 0. So x is equal to negative y, negative z. Y is equal to negative z. And z is s. So that's negative s. And the negative s minus s is negative 2s. So x, y, z is negative 2s, negative s, and s. If you take s as a common factor, you get negative 2, negative 1, and 1. Now we check v equals lambda v. If you multiply 3, where's a? If you do 1 times negative 2 plus negative 1 times negative 1 is negative 1. Negative 1 times negative 2 plus 2 times negative 1 plus negative 1 times 1 is negative 1. Negative 1 times negative 1 plus 1 times 1 is 2. Now if you multiply 3 by the eigenvector here, 3 times negative 2 is negative 6. Okay, that's not true. Then what's the matter? Did I do something wrong? I switched and then multiplied by 1, by negative 1. switch, then multiply by -1, then 2 times R1. Oh, sorry. لا عادي 2 times 1 plus 0 2 صح. Then I added these, I get a row of zeros. Then I do x plus y plus z. Oh, negative of 2s. Okay, I understand. Oops. That's negative, and y is negative s, so that's negative s, so that's s. You know? So negative of negative s is positive s. S minus s is 0. بس حتى ولو حتى هيك ما بتزبط. بس let's see. Okay, so that's a times v. Then we do lambda times d, so 3 times 0 is 0. I did something wrong, but where is it? It's -3. Did something wrong. Oh, that's 2, not z. Bruh. Swear to God أنا محشش. أنا عشان هيك بحط الزي. كيف بكتب الزي؟ بحط فيها شخطة بس ما بعرف شلون. تخيل يا أخي سبحان الله 2z. So that's 2s. So minus 2s, so that's 2s. 2s minus s is s. 2s minus s is s. So that's s negative 2s. So that's 1, -2, 1. 1, -2, 1. 1, -2, 1. Okay. Let's check now, please. بدنا نكمل بقى. لا على أساس أحل كمان شو recommended. hell no man. أنا السؤال واحد من previous مع 1 times 1 plus -2 plus 0 times 1 is 3 بشارة خير 3 -1 times 1 plus 2 times -2 plus -1 times 1 -6 بشارة خير 0 times 1 plus -1 times -2 بشارة خير. So that's a times v. If we multiply 3 times this, so we get 3 -6 is 3, which is the same thing. So that's v3. Let's go. Okay, after we find all of these, determine whether or not it's diagonalizable. Well, since we corrected this, the eigenvalues are all distinct, and since this is a 3 by 3 matrix, we have n distinct eigenvalues, then this matrix is diagonalizable. We can also strengthen this claim by, since we have 3 by 3 matrix and we have 3 linearly independent eigenvectors. This is eigenvector number 1. This is eigenvector number 1, eigenvector number 2, and eigenvector number 3. So there are 3 linearly independent eigenvectors for a 3 by 3 matrix, so that's another way to check. And the multiplicity as well, because this is lambda minus 1, lambda minus 3, so this the algebraic multiplicity of this is 1, algebraic multiplicity of this is 1, algebraic multiplicity of this is 1. For 0, its geometric multiplicity is 1, geometric multiplicity is 1, geometric multiplicity is 1, so the geometric multiplicity equals the algebraic multiplicity for each eigenvalue. So that's the third way of checking whether it is diagonalizable or not. So it's 100% diagonalizable. Okay. Okay, if it is, find a matrix P and a diagonal matrix D such that show it's invertible. Okay, fine. Matrix P is the matrix of 1, 1, 1. Show counter vectors. The matrix of the eigenvectors 1, 1, 1, -1, 0, 1, and 1, -2, 1. -1, 0, 1, and 1, -2, 1. Okay. That's matrix P. Matrix D is 0, 0, 0, 0. We have 0, 1, 3. The 0 corresponds here, 1 and 3. Okay. Next, what do we need such that A equals P, D, P inverse, show that P is invertible. P is invertible. Well, you can show this by, the determinant of P. So the determinant of P is 1 times 0 minus 2, which is 2, plus 1 times 1 minus 2 is minus plus 2 plus 1, 1. So that's 2 plus 3 plus 1, which is 6. So this 6 is not equal to 0 since it's invertible. And find AP and PD. So AP equals PD. Well, if you don't know, you can put it into a matrix here. Where's the matrix? Yeah, this one. And you enter it 3 by 3. 1, negative 1, 1, 1, 0, negative 2, 1, 1, 1. Again, you do matrix, you save matrix B, 3 by 3, 0, 0, 0, 0, 1, 0, 0, 0, 3. Then you do option, matrix A times matrix B. So that's P times D. So that's 0, negative 1, 3, 0, 0, negative 6, and 3, 1, 0. What about A and P? Well, matrix A is this, right? So I need to save matrix A as 3 by 3, 1, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 1. And we do option, matrix C times matrix P, which is matrix A. So that's 0, 0, negative 1, 3, 0, 0, negative 6, 0, 1, 3, which is the same exact. So that's finding this. Hence, A can be written as PED, P inverse. So you can write it as A equals, and to find the inverse, I think you can do option, identity, no, can't you do like matrix P was matrix A, right? Can't you do negative like this? It's syntax error. I'm not sure how to find the inverse of a matrix on a calculator. Press the and do not use the exponent button. Oh, okay, cool. So that's matrix this, inverse. Oh, nice. So that's matrix P, matrix D, I don't know where to put this, Salaha. Let's put it in a new slide, maybe. Matrix P, matrix D and the inverse, which is 1 over 3, 1 over 3, 1 over 3, 1 over 5, negative half, sorry, this is half, over 6, negative 1 over 3, 1 over 6. That's, so that's, sorry, that's matrix A. بس هذا هو السؤال. دايم أخذ معي شقد، أخذ معي ساعة. شيش. And how many, bro? That's a lot of work, Loki. It's basically the same thing. أنا برأيي والله ديم. We are cooked. ما شاء الله, ما شاء الله. Okay, we can solve this, I guess. I can solve this as well. show that this is to be honest والله تعبت أنا. I need to sleep. I have a quiz tomorrow. Sheesh. So that 2 is an eigenvalue of the matrix A and so on. Okay. Okay. So first, I will move fast now. Lambda 1, 3 minus lambda. Okay. So that's negative lambda والله بتعرف خلينا بدون مشاكل because this will take us بعرف صراحة خلينا هيك بدون مشاكل. negative 1 minus lambda times this is 9 minus 3 lambda plus lambda squared minus 6 lambda plus 9 minus 3 lambda minus 3 plus 1 plus 3 negative 1 minus lambda wait, this is negative 1 minus this is lambda minus 3 this 1 minus lambda plus 3. Okay, all of this is equal to 0 by the way, so that's negative 1 minus lambda وخلص على طول negative lambda squared minus 6 lambda minus lambda squared plus 6 lambda minus 9 minus lambda cubed plus 6 lambda squared minus 9 lambda plus minus 3 lambda plus 9 minus 3 minus 3 minus 3 lambda plus 9 equals 0. So that's 6 minus 1 is 5 lambda squared. So that's finished. 6 minus 3 is 3 minus راحت so that's minus 9 lambda minus 9 plus 9 راحوا 9 minus 6 is 3 so plus 3 and we have a negative lambda cubed here, so that's plus 0 because we said we want it to be positive, so multiply by negative both sides. Now for this, -1, -5, sorry, 1, -5, 9, -3, bruh. يا زلمة خلصني بقى. لا عاد كيف يعني؟ هي أنا حسبت صار هاي 1 -5 9 -3 bruh what؟ كيف مش 9؟ قال هي 8 وهي 4 كمان. يا أخي أقسم بالله خلص أنا تعبت والله تعبت حاج تعبت أنا تعبت ول يا أخي والله كويس طويل شو هاد علي الحلال يعني ما راح يخلص زي هيك. لو لسه في لابلاس كمان ما شاء الله ما شاء الله الله أكبر عيني ما تحسد الكوزات لا إله إلا أنت. Oh no way bro. في -1 هون يا أخي كل مرة يا أخي. هي -1 يا أخي. الله ينتقم من هدول -1. -1 so that's 8. والله بدي أنام أخوينا. 6 minus 8 minus 3 minus 3. Okay, that's minus 8. Minus 8 minus 3 minus 3 plus 9. This is minus 8 plus 9 minus 3 minus 3 plus 9 is 4. That's plus 4 and minus 4. هي ما بتترقع، لازم نكتبها هيك. اوكي هلا هون 1 negative 5 8 negative 4 lambda 1 equals 1 lambda 2 equals 2 وفي وحدة ناقصة. ممتاز جدا. هاي هلا لازم synthetic division، بعرف شو اسمها. So this is 1 negative 5 8 negative 4. This is lambda minus 1, so this is 1 مثلا. بننزل هاي 1. 1 times 1 is 1. Oh wait, we divide? لا ما divide, not divide. Yeah, I think so. 1 times 1 is 1. Hold up a second, let me see. No ما في شي فوق هون. نزل هاي. So that's 1. 1 times 1 is 1. Then you do negative 5 plus 1 is negative 4. Negative 4 4 4 0. So that's lambda squared minus 4 lambda plus 4. So now you get 1 negative 4 4. Then the 2 is the multiplicity. So lambda 3 is 2. Okay. So that is an eigenvalue of the matrix and solve. Yes, it is an eigenvalue of the matrix. And we solve. How do we solve this? كيف كنا solve? How do we solve this? Yes, we find the eigenvectors for each. Whoa, that's a lot of work. Negative 1 minus 1 is negative 2. I'm talking about 1 now. Three minus 1 is 2. So that's 2, 2. Next we row reduce. So first let's interchange row 1 with row 2. So that's gonna get this, and then this, then multiply by negative, so that's negative, negative, but this is positive. Then we do row negative 2, row 1 plus row 2. I see my whole life. Oh. Negative 2 times negative 2 plus 3 is 7. Yes, 7. So that's negative and positive here. يا أخي إيدي فيها حبة أعوذ بالله. Okay, negative 7 R2 plus R3. I see my whole life. Negative 7 times negative 1 plus 5. Then I do row 3 divided by 12, so that's 1. I see my whole life. Then I do row 3 plus row 2, so that will give me 0 here. And lastly 2 row 2 plus row 1. This will give me, where do I put this? Let's see. Yeah, we put it here. 2 row 2 plus so this will give me 0 here. And I can do row 3 plus row 1. Which will give me 110. So that didn't give me any eigenvector. The heck? Am I doing something wrong يا أخي؟ أقسم بالله why it's like this? X, Y, Z. This can't be. This can't be. Is this for one? No, I give up. Wallah, I give up. خلاص شو هاد? Swear to God, like what is this? I know how to solve بس يا أخي. خلاص I gave up. Just let's hope for the best. Thank you for watching يا جماعة.